The same PDF becomes 3 different documents depending on the parser. Benchmark Docling, Unstructured, and PyMuPDF with TEDs before broken tables poison retrieval. You'll learn how the pieces fit into a workflow that benchmarks document parsing and chooses a parser by tables, order, and speed. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Real projects ingest hundreds of PDFs, invoices, specs, reports. Tables hide the critical facts. And when a parser mangles rows or headers, your retrieval system returns the wrong answers. We need a repeatable way to pick the parser that keeps table structure and reading order intact, while staying fast enough to scale. A table-fidelity benchmark does exactly that. It compares structured outputs times each parser and measures how parse tables diverge from a human gold standard. Think of tables as trees. We compare the parser's tree to the ground truth tree. Closer trees mean fewer lost rows and more reliable cell alignment. The result is a single number you can use to rank parsers, plus a check that visible chunks follow human reading order. We'll build a small benchmark that sends one PDF through 3 parsers, computes a structural score per parser, checks visible reading order, and picks the best parser by score, order, and latency. That pick is what prevents a broken table from poisoning a retrieval pipeline. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Now we start by defining the benchmark case and a gold standard for one PDF. This snippet defines the benchmark case, expected table HTML, and reading order anchors. Teams usually start parser tests with a PDF path, but the benchmark needs ground truth too. Otherwise, every parser output just looks plausible. The truth HTML value is the table structure we expect, while case order captures the visible sequence that retrieval chunks should preserve. Corpus keeps those pieces together, so later steps can reuse one source of truth instead of scattering paths and labels through the notebook. The visible output confirms how many PDFs are entering the benchmark. Now that we have a ground truth, we need a first parser run and a basic timing measurement. This example runs Docling on the same PDF and captures its first table as HTML. A clean demo often stops at Markdown, but table fidelity scoring needs a structural representation. So doc.tables.export to HTML doc becomes the comparable artifact. Perf counter starts the latency measurement before document converter. .convert path and stores elapsed time in times. The parser output goes into runs, which becomes the shared result dictionary for the rest of the benchmark. The visible output shows Docling found a table, which is the minimum signal needed before scoring fidelity. Docling gave us one view. Now we add the other parsers in the same shape and measure their times so comparisons stay fair. This code adds unstructured and PyMuPDF outputs beside the Docling result. Unstructured uses partition PDF with strategy high res and infer table structure equals true. So table elements can carry metadata text as HTML. PyMuPDF opens the same file with PyMuPDF open, finds the first table through find tables, and converts it to HTML through the pandas bridge. The important move is not declaring a winner yet. It is forcing all parsers into the same runs shape and timing them in times. The visible output shows the benchmark now compares 3 parser results. With 3 parse table HTMLs, we need a structural metric that catches dropped cells and misnested rows. This snippet turns extracted table HTML into TED scores with BeautifulSoup and APTED. Broken tables are not just bad text. They change rows, headers, and cells in ways that hurt retrieval and answer grounding. SIG parses each table with BeautifulSoup and builds bracketed trees from table-related tags. Then APTED measures tree edit distance against the gold structure. TEDS converts distance into a similarity score, and scores keeps one rounded value per parser. This compact version scores tag structure, not cell text content. The visible output shows the strongest table structure score available in the run. Scoring is only part of the decision. We also check whether the parser preserved the page reading order and how long it took. This example combines TEDS, reading order errors, and timing into a production parser choice. A parser with a good table score can still fail RAG ingestion if the visible sequence is scrambled. So read errors checks the anchor order from case order. The pick expression ranks by higher scores, then fewer orders, then lower times, which mirrors a practical ingestion trade-off. The HTML cleanup is intentionally small because the parsers already produced structured table outputs. The visible output names the selected parser, its reading order error count, and its measured parse time. In a real project, this toy benchmark maps to an ingestion gatekeeper. Run it on a representative set, say 100 invoices, and use the chosen parser for downstream chunking and vectorization. Keep the same truth tables as a regression suite, so parser upgrades never silently break retrieval. What this is: a targeted benchmark that compares table structure, reading order, and latency to choose a parser for RAG pipelines. When to use it: before you ingest documents with critical tables, especially invoices and specs. One caveat: TEDS measures structure, not semantic cell values, so pair it with text checks if exact cell text matters. To extend this work, tune the pick ranking by increasing the penalty for read errors and testing different TEDS thresholds across a validation set of 100 PDFs to find the best balance of fidelity and speed. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.